Hello, my name is Dr. Freya Addison, and today I'm going to be talking about how radar shines a new lens on the vertical profile of flying ant day. I'd like to thank my colleagues, Liz Duncan, Tom Daly, and Neely from the University of Leeds, who were instrumental on this project. Oh, and please consider me for the Anne Kiemer Prize. So I'll just briefly go over what we're going to be talking about. So I'll do a brief introduction on Flying Ant Day, and then onto radars and why we should be using them for insects, and then how radar sees ants, so the radar cross-section of ants, and then the biomass and altitude of Flying Ant Day, and then a summary. It's going to be a little bit of a whistle-stop tour, but please find me for questions. I'm very happy to chat. So, Flying Ant Day. So, I am a physicist. I'm talking to an entomological audience, but I will explain as best I can about Flying Ant Day. So, in the UK, we have something called Flying Ant Day, which is a little bit of a misnomer. We have more than one day. We typically have at least 5 days per year in the season June to September, or 97% of flying ant days occur between July and August. Thank you, Dr. Adam Hart, for that. And what this happens, this is a nuptial flight, this is a mating flight. So the queens give birth to new queens and lots of males, and they take off, go in flight, mate with other colonies, and then they disperse, and then the queens will fly back down, burrow into the ground, and establish their own colony. When I am talking about ants, I am typically referring to Lasius niger, but Lasius flavus also is another common species in the UK, which will also have typical behaviours. The males die, so they either get eaten up in the air by birds, or they become part of the nutrients and an important part of the nutrients of the ecosystem when they come back down to the ground. Lasius niger is considered cosmopolitan, so that means we expect to find it all over the UK, whether it's kind of in the city, in the suburbs, or out in the countryside. Again, a good reason to study it. So, Met Office radars. I'm going to switch track a little bit. So, meteorology, weather. In the UK, we have 15 radars which are operated by the Met Office, and then we have 2 in Ireland. They're all dual polarization, which means they emit radiation in both the horizontal and the vertical, which I'll explain in a moment. The time resolution is we run 24/7, and they scan every 5 minutes. And they do go up in several elevations and do a big circle. And that means we have amazing spatial coverage. And so the light blue, so the red dots are the radar, the light blue is about out to 200 kilometers, and the dark blue is the 50-kilometer range, which is typically where I expect to see most of our biology. As you go further out from the radar, your beam volume gets bigger, and so when you're looking at things which are small and less dense, then it becomes harder to identify things. So what is radar? Radar is radio detection and ranging. So it's operating in the radio part of the spectrum. In the UK, the Met Office operate at C-band. So the antenna emits a wave. The wave hits a target, whether that be a plane, a cloud, or an insect. The dish picks up part of that reflected energy, and then that. So you can see this big dish. This is Gibraltar Observatory, which is a research radar. So the dish picks up that reflected energy, and then that's recorded, and we identify what it is. How do we identify it? So I mentioned dual polarization. So the wave is both horizontal and vertically polarized. I think we got that in the wrong directions there. And so since 2017, 18, the Met Office completely upgraded their system. I think it started even a bit older. So some areas from 2015, we have dual pole radars. And this tells us so much more information about what we're seeing. Now, with the development, we know very well about snow, hail, rain, different mixes, compositions. We got algorithms for the meteorology, and then we sort of like we categorize them in different things. So this is meteorology and this is clutter. Part of that clutter is biomass, and then there's been some work done, particularly in Europe, separating birds. So there's birds, and then we've got this other biomass thing. And this is biomass is what we're starting to sort of delve into and try and get to the bottom of what that is. I highly recommend my colleague Marina Luca's paper, also from the University of Leeds, about clustering and kind of trying to separate those a bit. But yeah, how do we know what each thing is? So each thing has its own fingerprint, its own unique identifier to tell us what it is. And so when we get that target back and that data, we can kind of compare it to a list, a lookup table almost, and we look at the different properties to try and identify where it's going to fall. And what we want to establish is where it's going to fall in the biomass category. And this is the algorithms we want to learn about and do more with. My focus today is on flying ants, but I want you to think about the bigger picture here. So what's one way we can establish a fingerprint? It's by modeling. So back in 2020, I did a lot of research on this, and I was working with a Lepidoptera moth, and I published a paper which is linked DRI there. So yeah, look up Freya Addison Lepidoptera radar cross-section. And typically, when biomass has been modelled before, ellipsoids we use. They were like, okay, we're going to fill this with like insect goo, that's the density. And this is what it looks like in a radar. Okay, roughly, that's that. Different species, different that. Okay, good. And we're like, is that the case? No, it's not. So we used highly high fidelity anatomical scans. And in 2022, we published a paper, and we found that not only did the anatomy matter, kind of the different densities, the different parts, like the different shapes and stuff, and wings matter, and they do not look like an ellipsoid. So we did the same for the ants, and we discovered something else. So for ants in particular, so the photograph shows the queen, which is the big one, because she's around, her fresh weight is around 26 milligrams, and then the male is about 3. And so big size difference, just like physical size and weight. And then on the graph, there's a big difference between the blue and the thing. What I really show you is this is the difference the radar sees. So the radar is quite crude. It will see the biggest thing, which could be like a big metal object, highly reflective target. It's going to see the biggest thing, the most reflective thing, or the thing that there's most of. Okay, so when we're looking at this, we've got our queens, ants. So we've got our queens, which are looking like an emperor penguin, the size of an emperor penguin, and our little males looking like an ant. The radar's not going to see the ant, it's just going to see the penguin. So the ratio of from literature is about 20% queens to 80% males, give or take. But still, when you put like 80 ants and 20 emperor penguins, you're just going to see the penguins. So that's what the radar's saying. We're just seeing the queens on Flying Ant Day. So, Flying Ant Day, citizen science. So we ran a survey between 2020 and 2023. The key years were 2021 and 2022, where we got 5,000 respondents. We took the first part of their postcode as their location, and we got every postcode in the United Kingdom. Fantastic. 5,000 is not population significant, but it was good having that spatial variation, and we chose 100 respondents would give us a flying ant day. So that was a really good kind of way to like distinguish that. So this is the culmination of all the work. So the colours, we've got number density per kilometre cube. So that ranges from, my face is covering it, from 10 to 3 to 10 to the 8. 10 to 3 is 1,000 and 1,000 ants, and then we've got 10 to the 8, which is 100 million ants per kilometre cubed. Now, you can see this wonderful animation, and there is filtering that needs to be done. There was some filtering, but this is for the elevation, sorry, not elevation. This is for the altitude between 1 and 1.5 kilometers. There is, you see a big circle by the radars, and that's just because we're at a certain elevation. So as you go further out, we get to that elevation and things. So if we're looking at lower elevation, we would have rings closer to the radar and things. So that's why we've got big gaps. And yeah, there needs to be some filtering done, but the most interesting thing is the features. So we've got lots of activity happening here. If you can see my mouse, we've got these lines which are broadening out. We've got little clusters which come up, and we've got these circles which expand in different areas. And what I'm going to show you next is how that looks from a vertical point of view. So vertically, so this is biomass of an afternoon cluster. Please ignore the numbers. They are wrong, but the rest of it is right. The colors are right. It's just the units a bit off. So we are going up to 2 kilometers here. I want you to focus on the yellow green. Isn't it beautiful? And we can see we've got high density up here and in this kind of circular column. So we're looking at kind of a thermal here, and then it turns into this teal. So that means we're dropping down in density and it's dispersing. Okay, and that's really important. So what we're also been looking at, what we're currently doing, preparing for a paper, is looking at how we can relate this to sort of environmental information, so land use. And again, this is something that I want you to think about for how to use radar for aeroecology. So one of the things that particularly stood out for us was peat bogs. They had significant correlation with ant emergencies and things like that. So that was cool to find out. And this is something we're just currently studying. I'm going to give you a rapid result summary. So altitude. We regularly see, and every single flying ant day, we regularly saw them like up to 5 kilometers. That's where like all the activity was. First 5 kilometer boundary layer between 1.2, 1.8 in the summer, but we're going beyond that. First 5 kilometers, and every single flying ant day we would see ants at 8 kilometers, and we saw swarms even beyond that. We had biomass, which was between 50k and 500k kilograms, which includes background biomass. So yeah, but the biomass was so significantly more than you would get on the other days. It's just not comparable. Yeah, there's anyway. Density, we're looking at sort of our range was between 10 to the 3 to 10 to the 8, so where we had activity. So we're getting like kind of a background sort of level of around 10 to the 4 to 10 to the 5, and then we had like bigger and smaller peaks and things like that, different dispersal rates. And then yes, for the radar cross section, our little fingerprints, ant wings are not visible for C-band radars, where they are for Lepidoptera. If you have a stationary, a kind of stable, high pressure system sat over the UK for at least 2 days, that you're going to have an emergence of ants between June and August. Radars can track swarms, if you can see, and this is the first time all of this has been done for Flying Ant Day, so that's really cool. So, before I run out of time, this is what we're going to do. Future work, publish, please consider me for the prize. And yeah, please just ask me questions. I can't wait to talk.